Welcome back. In this video we'll be building a simple non-latching intruder alarm using a piezo style buzzer, a single pole double throw 5-volt relay, a diode, a PNP transistor, a few resistors, and a momentary button, as well as a 6-volt power supply. What makes this circuit different from the norm is that it's a sort of break to make style circuit, and that's due to the way a PNP transistor functions. Just to demo that, this circuit alerts, or the piezo buzzer sounds off, when the momentary button is not pushed. This is a normally open momentary button. So when this button is open, the buzzer sounds. And when this button is closed, the buzzer doesn't sound. Just as a demonstration of how that works, is with the button pressed, no sound from the buzzer. Release the button, and every time the button is released, the piezo buzzer sounds off. And one can immediately probably imagine that all it takes is to arrange the world in such a way that whenever your door is closed, something is pressing down on this momentary button, and that will be enough to keep the piezo from sounding off. And then as soon as someone opens the door or walks in, and whatever it was that was pressed against the momentary button is released, then the piezo sounds off. It's an interesting circuit. It's non-latching, and what that means is that it only alerts or only sounds off as long as whatever is pressing against the momentary button is not pressing against it anymore. As soon as something presses on it again, it shuts off. This is a lot like when one walks into a convenience store or a gas station and a certain little dinging sound occurs while the door of the store is open, but as soon as the door of the store closes, the dinging sound goes away. That's this setup. Let's look at the schematic and build the circuit. The schematic for this circuit is fairly straightforward. We'll have a momentary button with 2 resistors, a PNP style transistor, as well as that single pole double throw 5-volt relay, and a piezo buzzer. We'll have a diode thrown in to catch the back EMF from when this coil of the relay is energized and then de-energized. But beyond that, there's not much to this circuit. It's important though to kind of understand how it functions, especially with that PNP transistor sitting in there. So let's walk through the 2 states that this circuit can be in. Namely, when the button is not pressed versus when it is pressed. We'll consider the simpler of the 2 cases first. The state when the button is pressed, that momentary button is being pushed down by whatever one has mounted to the door or the window, etc. When this button is pressed, what happens in this circuit? Well, you have 6 volts that will travel across these 2 contacts. There's a fork in the road. Can deal with a 10K or a 1K. Voltage current's lazy. It'll go the path of least work. So it'll travel here and keep the base of this PNP transistor will be high. In a sense, this is like a pull-up resistor on the base of this PNP transistor. And recall that a PNP transistor only conducts when its base is 0.6, 0.7 volts lower than whatever voltage supply is connected to its emitter. Note, the emitter of the PNP is at the top toward the 6-volt supply. The collector is toward the load. All of this. In this context, that 6 volts will be keeping the base of the transistor high. And given that it's a PNP, that means this transistor won't conduct. PNPs, just like NPN transistors, they leak a little bit, so a little current might trickle through, but not enough to energize the coil of this relay. Speaking of the relay, what's happening when the button is pressed? Well, we know that the coil's not energized because the PNP, the base of it's held high, so it's not conducting, meaning no currents flowing through the PNP. That means that no current will be flowing through the coil of the relay either. It'll be de-energized. At that point, the flipper inside the relay, where will it be pointed? Well, toward its normally closed position. Like relays always have a normally open pin and a normally closed pin. typically at least in the context of a single pole double throw relay, that there are two throws, a normally open throw and a normally closed throw. Well, the normally closed is just like it says. This is where this little flipper lives its life until the coil is energized. Given that with the button pushed, the coil is not energized, the flipper will be pointed toward the normally closed contact and in turn normally closed pole. And what is the result of that? Well, there's no voltage supply to the normally closed, so we have no circuit. We have the normally closed pole through the flipper down to the piezo to ground, but there's no voltage that will reach the piezo, so it won't be sounding off. It won't be making its noise. So when the button is pressed, the base of the PNP is pulled high, making it so the PNP does not conduct. It won't switch on. And if it's not switched on, the coil's not energized or switched on. And with the coil not switched on, the flipper and the relay will be at the normally closed position, making no continuity between the piezo, which is connected to ground, but it won't be connected to a positive VCC or voltage, so it'll be off. That's the simple state to explain. That's what's happening in this circuit when the button is pressed. For the more complex state, the state in which the button is released or it is not pressed, what's happening in the circuit? Well, there will be no continuity between these two contacts, so we could ignore that 6 volts. So all we have to worry about is what's happening at the base of the PNP in this context. It has a 1K, 10K to ground, effectively pulling the base of the PNP low. Remember that a PNP, it conducts or switches on when its base is 0.6, 0.7 volts lower than whatever voltage is connected to its emitter. In this case, it'll be 6 volts. Well, the base of this PNP transistor, given that it's connected through a 1K, 10K to ground, will be significantly lower than 6 volts. That'll be enough to make the PNP conduct. So we'll have current that'll flow through the PNP, then it'll flow to the coil, energizing the coil. That will in turn, and then once it energizes the coil, it'll go on the ground. But when this coil is energized, that'll cause the flipper inside this single pole double throw relay to flip from the normally closed state to the normally open state in making a connection here. And as soon as this connection is established, well, we have 6 volts through this path, past the flipper, through the piezo to ground, making the piezo sound off. That's how the circuit functions in the case where the button is released or it's not pressed. That as soon as the button is released, the base of the PNP is pulled to ground. As long as that base is 0.6, 0.7 volts less than whatever voltage supply is sitting on its emitter, then the PNP will conduct. Well, the base being pulled through the 1K, 10K to ground, that'll make it significantly lower than 6 volts, making the PNP conduct. The current will flow through, energize the coil, throw the flipper in the single pole double throw relay down to its normally open pin, closing that pin to the PNP, and we'll have 6 volts through the normally open pin, through its contact, through the flipper, through the piezo to ground, making the piezo buzz or screech or whatever you want to say. That's how it functions when the button is not pressed. Let's build the circuit. To get started, I've connected both of the power rails of the breadboard through these wires, as well as the upper rails to the lower rails through these pieces of wire. I've added a normally open momentary button to the board, a PNP transistor, as well as our single pole double throw relay. Let's look at that single pole double throw relay just to get a sense of how it's oriented in the board. So I've put this relay in the board, and note the one that I'm using, I picked it up from RadioShack, but the part number's on the schematic, as well as I'll put it in the description of the video. But it's just a simple 5-pin single pole double throw 5-volt relay, and you can compare the 5 pins with this mini schematic that I've drawn and stuck to the top of the relay in the board. There's the relay in the board. And the way to understand it is when you're looking at the relay, you'll have your bottom pin by itself. There'll be no pin next to it. There'll be 2 pins on one side, 2 pins on the other. And then if you take that relay and you roll it over just like that, then that's how this schematic would apply. If you use a different part number, single pole, double throw, 5-volt relay, then your schematic may be different than this. But this just gives you a sense of how you would go about figuring out the schematic for it. The data sheet may have the schematic, and it very likely would for whatever 5-volt relay you select. But normally the pinout in the schematic provided in the data sheet will be with you looking at the bottom of it, with the pins facing you vertically up toward your face. Well, that can be kind of confusing as soon as you have to roll the relay over to stick it in a breadboard or on a proto board. And to this day, I still draw it out. Either maybe not stick it and adhere it to the top of the relay like this for demo purposes, but I still always look at the schematic, roll the relay over, and then redraw the schematic, just so I don't get confused when I'm trying to hook it up. That's just a little tip. Maybe it'll be helpful, maybe it won't, but that's how I do it anyway. Let's zoom back out and look at our schematic again. Looking at the top of our schematic, the first thing we'll need to do is connect the upper right hand corner of our momentary button to the 6-volt power rail. We have the upper right hand corner of our momentary button. We have a piece of wire. We need to connect this corner of the button to the power rail, like that. Next, on the lower left hand corner of our normally open momentary button, we need to have a 10K resistor going to ground, and then a 1K right ahead of that 10K pointing down the breadboard toward our PNP transistor. Have our 10K. We need to connect the lower left hand leg of our momentary button through the 10K, pull it to ground. Like that. Then we need to take our 1K, and in this same row, add our 1K pointing down toward our PNP transistor. Coming off of that 1K, we need a piece of wire to the base of our PNP transistor. A piece of wire connected in. One end of it will be in the same row as the 1K, and then the other end will connect to the base of the PNP. The base will be the middle leg, at least on the PNP I'm using. And that's how it'll look. Note that if you use a different PNP, I'm using a 2N2907. You could just as well use a 2N3906. But you'll definitely want to check your pinout on your PNP. If it's a TO92 package like this one, normally it's perfectly fine to just take the black lead of your multimeter, touch the middle leg, take your red lead, touch one outside leg, write the reading down, take your red lead, touch the other leg, write the reading down. Whichever of the 2 legs has the highest reading will be your emitter, and with a PNP, you'll want your emitter, in the case of this circuit, pointed back up toward that momentary button. And the collector of that PNP, it'll be in the direction of the relay on the breadboard. Going back to our schematic, at this point we have 6 volts to the upper right hand corner of our momentary button. On the lower right hand corner of our momentary button we have a 1K through a piece of wire to the base of the PNP, as well as in the same row as that lower left hand leg of our momentary button we have a 10K going to ground. The next thing we need to do is connect the emitter of the PNP to 6 volts. We have a piece of wire, and the emitter of the PNP is this upper leg. So in that row, there's the leg. We need to stick one end of our wire and then carry the other end over to the positive rail in our breadboard. Like that. The emitter of the PNP through a piece of wire to the positive rail of the breadboard. There's the orientation in respect to the momentary button. With the emitter to 6 volts, now we need a piece of wire on the collector going down toward this pin of the coil on our single pole double throw relay, the upper pin. And we'll also need a diode with the cathode pointed up toward the PNP. And this diode is just to dissipate the EMF, or the electromagnetic field, that will be generated when this coil is energized and then de-energized, or it collapses. This just provides an alternative path for that voltage and current to dissipate rather than feeding back up and blowing out the PNP. And that's all that diode is doing. It's just for a safety feature. So we need a piece of wire from the collector of our PNP to the rail that the upper pin of our coil is in. Then we'll need a diode with the cathode pointed toward the PNP. As well as, while we're here, we'll need a wire for the second pin of the coil to ground. Let's put that in. Okay, there's our emitter of our PNP pulled up to 6 volts. This would be the collector of it. There's its collector. What we need is a piece of wire from the collector pin of this PNP to this upper pin on our relay's coil. We need a piece of wire from this rail to this one. Like that. Now we need a diode. I'm just using a small signal diode. You could just as well use a 1N4001. I'm using a 1N4148, just a small switching signal diode. And the cathode on this kind of diode is marked with a black line, and we'll want the cathode pointed up toward the direction of that PNP. And it needs to straddle the 2 pins of the coil. Like that. The final thing we'll need is we need a wire in this rail, where the same rail that the anode of the diode is in that rail to ground. Like that. We have our wire from our collector of our PNP coming down to the upper pin of our coil. We have a diode to help dissipate the EMF that will be generated when this coil is energized and de-energized. The cathode of this diode is in the rail with the wire coming from the collector of the PNP. The anode of the diode is in the bottom pin of our coil in that rail, and then it has a wire in the same rail as the anode to ground. We're almost done. We just need to add in just a few more wires. First, we'll need a wire from the 6 volt rail to the normally open pin of our relay. There's the normally closed pin of the relay, would be in this rail. It's normally closed. How do you know? Well, the flipper on the schematic will be pointing toward the normally closed pin. And then directly underneath the normally closed pin will be, in this context, is the normally open pin, the pin that the flipper is pulled away from. So we need a piece of wire in this rail of the breadboard to VCC. It's really easy to make a mistake with this on these sort of micro mini 5 volt relays. So it's easy to end up with one wire that you wanted on the normally open pin actually on the normally closed, or vice versa. So we need a wire here, normally open pin is in this rail to VCC. Just like that. Normally open pin, the rail that it's in, with a piece of wire to VCC. Here's the wire we just added, 6 volts, normally open pin. Now we need to finish out the circuit. On what's often referred to as the common pin, or this is what I tend to call the pole pin, is the one that your flipper is connected to internally inside the relay. But on this pin, we need the positive wire from the Piezo Buzzer, in a sense, piezo would work either way. Most of them will, but we'll just be consistent with it has a red wire, so we'll need its red wire connected to this common pole of the relay, and then the black wire of the piezo to ground. We have our piezo with its red wire. We'll want to connect its red wire to the common pole of our relay, the leg that the flipper is connected to, and then the other wire, its black wire, to ground. Zoom out so that everyone can see. And if we've done everything right, we should be able to hook in our 6-volt power supply, and when we're pushing the button, the piezo should not sound. When we release the button, the piezo should sound. Alright, let's push our momentary button, lock in the battery, and when we release this button, the piezo should alert. And it does. It stops when we push the button, it sounds off when we release it, which is exactly what we wanted it to do. As a final comment, some viewers may have been wondering, I'm using a 5-volt relay, yet with a 6-volt power supply, and they may be wondering, what's up with that? Well, the simple answer to that is that this 5-volt relay, and most 5-volt relays, the coil is rated for more than just 5 volts. The coil of this relay, according to the data sheet, can go up to 6.5 volts max. So running 6 volts through the coil of the 5-volt relay is perfectly fine. It doesn't hurt a thing. And the alternative would be to use some sort of voltage regulation circuitry, say a LM7805 voltage regulator with a 9-volt battery that's pushing 5 volts out the other side. The downside to using such is that that voltage regulator will draw a certain amount of milliamps even when this button is pressed and be killing your battery. Whereas if you just use 6 volts with this particular circuit, when the button is pressed, there's positive voltage going to the base of that PNP, and there may be a little conduction here, but not really enough to even matter, and you'll have a whole lot less battery drain with the 6 volts than you would if you had a voltage regulation set up in this to go from 9 down to 5. And it's perfectly safe given the rating of the coil. That's just for those who might have been wondering why 6 volts with a 5-volt relay. I'm going to mount this circuit rather crudely to a door in my house just to give people the final idea of how you could mount this in a way to trigger when someone opens the door. As mentioned, this is clearly a crude way and set up to mount the alarm, but all that I have is the breadboard mounted around the seal of my door with a ruler pressing down on the momentary button so that anytime the door is open, the momentary button is released, sounding off the piezo, and whenever the door is closed, the momentary button is pressed again, turning off the piezo. Just so very similar to the setup you have at a lot of gas stations. Right now, it's in the state where the momentary button is pressed, so the piezo is not making any noise, but if someone were to open the door, it would sound off. Clearly, like I said, it's crude. You would want to do a better job of mounting it, hiding your button, hiding your circuit. And the main downside is that it is non-latching, so that if someone opens your door really quickly and then closes it right back, the alarm will go off for the length of time the door is open, but it will immediately shut back off as soon as the door or the window is closed. In a later video, we'll look at how to make a latching version of this circuit so that the alarm turns on and stays on even if the door or the window is closed. But that's for a future video. This at least gets us started. I hope it's been helpful. If so, please consider clicking like and also consider subscribing to my channel. Thank you.